Fair enough. Thank you very much. Welcome, everybody. You chose this, so it's your fault if you don't like it. I thought we'd talk about software engineering. If you ply me with beer, which I am wont to take, then occasionally I will wax lyrical on the subject of software engineering, and that I think that what we've generally discovered in recent times is a proper engineering discipline for software development. So I thought this presentation is a conference presentation that I've used a couple of times that kind of explores that idea in a bit more detail. And I want to talk a bit about what I mean by engineering, what really works for engineering, and so on. I think I don't see anybody who looks quite as old as I do in the room. But if you've been around for a long time like me, there's been various takes on what engineering means in software over the years. I started out my career with job titles like software engineer and stuff like that, and we were doing no engineering. Nothing was close to engineering in what we were doing at that point. And then I started working in environments where that became less fashionable. It wasn't really fashionable to refer to ourselves as engineers, and we started adopting terms like software developer and senior software developer and stuff like that instead, which was probably a bit more accurate. It was a bit more truthful in terms of the sort of things that we're doing. And then I had the privilege to work on a project where I think that we did start doing some real engineering, and the difference was quite dramatic. And that's really what I want to talk about. So let's start off by thinking about what engineering is and what software engineering is. Certainly, to my mind, when we start using the terms like software engineering, it conjures up pictures like this. This is to software engineering what a soldering iron is to electrical engineering. It's a tool. This is not software engineering. It may be a useful tool. In this case, it doesn't look like a very useful tool, but it might be. But it's certainly not defining a practice. We can think about kind of project management disciplines, and this is the Scrum process. Anybody, any idea how many times the Scrum process, the documentation for Scrum, mentions the terms software or code? None. None at all. So it's a good project management discipline. I'm not knocking Scrum. It's a good project management discipline, but it says nothing about the engineering practices that are important. It's as applicable to plumbing as it is to software development. It's good for plumbing. So this isn't software engineering either. In recent years, certainly in the sorts of organisations that I inhabited for a while, the term software craftsman and software craftsmanship has grown in favour. And this, I think this is for some good reasons, which we'll go into. But I don't think this is enough either. Craftsmanship is not the same as engineering. Craftsmanship is important, it's valuable, but it's not enough on its own. And I'll explain what I mean by that in a bit more detail. One of the ways of looking at this and exploring this problem is to think about the history of production for human beings. And I think that pretty much all production breaks down into these three categories. It's probably a bit overly reductionist, but there you go. For much of human history, everything that we made was the output of a craft-based process. Productivity, quality, all those sorts of things were variable depending on the craftsperson that was building things, but it was essentially a craft-based process. Around the middle of the 19th century, mass production became popular. The first real use of mass production wasn't in automotive industries, which is commonly thought. It was actually building rifles for the American Civil War. One of the horrific parts of the American Civil War was that that was the first war where the production of armaments was truly mechanised. There's a nice story. If you can have a nice story about something as horrific as a war, there's a nice story about the man who wanted the contract for making the rifles for the northern states. And he went into Congress with a bag of component parts, and he put them on the floor, and he got the congressman to select components from the bag, and he assembled a rifle from all of the pieces. That was the first time in history when that was possible, because up until that point there was no real standardisation. So mass production kind of brought the ability to standardise and the ability to move quickly forwards with quality It revolutionised, really, the approach to making stuff. And then at the end of the Second World War, we started applying a little bit more science and a little bit more scientific rationale in terms of the approach to process, and lean production kind of took over the world of making things. Most modern factories making stuff these days are organised along lean principles: just-in-time delivery, just-in-time manufacture, just-in-time warehousing, all that kind of stuff are ideas that tend to flow from lean. So let's look at each of those in a little bit more detail. So craft-based production is art rather than science. It's down to the abilities of the craftsperson and the quality of their work. There are no work standards. It's just down to the individual or group of individuals. Each piece of work is individually handcrafted and is therefore unique. When I was talking about the example of the rifles before, prior to that event, if you bought a rifle and you wanted it repaired, you probably took it back to the person that built it. When you bought your rifle, it probably came with a mould for bullets because the bullets were unique to your rifle, because everything was uniquely handcrafted. And all of this was kind of based on individual expertise. The downside of craft-based production techniques is it's so variable in quality. We have a kind of emotional attachment to crafts-based things. If we're very wealthy, we might have hand-stitched leather in our cars or in our handbags or something. That's kind of common. But actually, in reality, it's not really high quality. Imagine for a moment a craftsperson-built iPhone. It doesn't really make much sense. You can't build something like that without deep engineering expertise and discipline. You can't create, even as a prototype, you can't do something like that. So crafts-based production is kind of interesting. It's kind of emotionally nice to think of it in those terms, but it's not really going to produce high-quality stuff. Mass production is quite good. It introduces assembly lines, standardisation of components, standardised steps, so that we're going to recreate those components, and piece-based metrics. We measure the progress through such a production process by how many bits we've made. And that lasted, that was effective. That was part of the generation of the Industrial Revolution, certainly through the early parts of the 20th century, as that took speed. Lean production is really about quality at source. It's about pull-based systems. If you think of mass production, you're kind of building components and effectively you're pushing them down the line until you've got enough to assemble something. And you have big warehouses to store your components and stuff like that. Lean is different. Lean is about just pulling the things that you need in time, and that's where these ideas of just-in-time delivery and just-in-time manufacture come in. Lean talks a lot about minimising the amount of work in progress so that we can kind of figure out what's going on, and we're minimising waste through the process so we can make the process efficient. So where's the software industry? Sorry, I was getting ahead of myself. Another take on this is of looking at processes in kind of their pure form. And one of the disciplines that's really effective of this is chemical engineering. If you think about it, the job of chemical engineers really is to productionize a process of some kind. So so they have a taxonomy of different kinds of processes. Here is one of their process, what they call process models. The defined process control model requires that every piece of work be completely understood. Given a well-defined set of inputs, the same outputs are generated every time. A defined process can be started and allowed to run until completion with the same results every time. Hands up all of those people who think that sounds like software development. So I'm not so sure. So this is the space of mass production, assembly lines and waterfall processes. I think this is not, personally, I'm sorry to disagree with you, I think this is not the way that software development works. This is, if with the same team, if we started off with the same set of requirements and we started off, a year apart, the production would be different. It wouldn't be the same. You wouldn't produce the same stuff. You get different stuff out the back end of the process. The other process model that's interesting in this context, I think, is this one. The empirical model of process control provides and exercises control through frequent inspection and adaptation for processes that are imperfectly defined and generate unpredictable and unrepeatable outputs. I think, to me, that sounds much more like our game. That's much more like the sort of world that we tend to inhabit. For me, software development is always a process of exploration. We are exploring the problem domain to understand it more deeply, and we're exploring the solution domain to understand whether our solution fits into and is useful within the context of the problem domain. It's a learning exercise. This is the territory of craft-based production. Craft-based production is really good at this kind of thing, which I think is one of the reasons. So first thing I should say is that to me that sounds much, much more like our kind of problem. In terms of software development. And craft-based production is a good technique for these sorts of problems, except it comes with the cost of the variable quality that I was talking about before. It's also the space of exploration, continual improvement, and lean process. So where is the software industry? I think we are nowhere close to mass production, and we never will be. It's the wrong model. We've tried to make it look like that, but mass production is for solving problems in production. We don't really have a problem in production. For us, production is pressing the button that says go on our compiler. That's production. Production for us is next to free. So production isn't our problem, it's design that's our problem. I think we are here. I think where we are is that we are a craft-based industry. And I think you can see that in the data. There's the amount of variability depending on the experience and skill of individual teams. The whole variety of indicators suggest that that's where we are at the moment. And I think that where we should be shooting for is here. I think we should be looking to sort of figure out how to start to adopt a little bit more, for want of a better term, discipline and rigor in approach to output higher quality, to get higher quality results. So if software projects were normal things, I think that there ought to be a normal distribution of software of success. As many software projects ought to finish ahead of schedule, under budget, delighting their users, as finish behind schedule, over budget, and annoying their users. But I don't think it's what we perceive of as normal. I think we tend to think of the curve that we tend to think of software development is much more weighted like that. And that's telling us something profound. I think it's telling us that we have the model wrong for software development on the whole, for much of the industry. I think when we start to get the model more closely aligned, we start to see quite dramatic changes in the effectiveness of our approach. We're often talking about orders of magnitude differences. We're not talking about small 5 or 10% improvements in quality, productivity, efficiency, and so on. We're often talking about massive changes. We can even say things definitively in terms of the data, like organisations that practice this kind of more disciplined approach to software development make more money than organisations that don't. We've never had data like that in the software industry before. For some reason, when I start talking about engineering to people, I get into a lot of conversations about bridges. I'm not quite sure why that is. Everybody says, yeah, but it's not bridge building, is it? Well, no, it's not bridge building. But I also think that that's falling into the trap that we software developers tend to fall into, which is oversimplifying other people's jobs sometimes. And if you are building a brand new, innovative kind of bridge for the first time ever in the world, that's a very, very, very different exercise than if you're building the same old suspension bridge that we've been building for a couple of 100 years. It's a different kind of problem. And in software development, we are much closer to the first kind of problem in everything that we do every time than we are for the second one. Because as I said, production isn't our problem. Reproducing something isn't our problem. It's the unique design of a new machine to solve new ideas that is our problem. The other thing that's kind of interesting is that when we start thinking about this, engineering is not all the same across other disciplines either. Bridge building is not, engineering in bridge building is not the same as the engineering in house building. It's not the same as aerospace or electrical engineering or chemical engineering. Each discipline brings something of its own to that discipline. Chemical engineering is its own thing. So I think one thing that we could be certain of for any engineering discipline that we can genuinely call software engineering is it's going to be ours. It's going to be our thing. There are going to be aspects of it that are unique to us. There's another way in which engineering is not all the same as well. Engineering is not the same at different scales. These are both engineered structures. And it's obvious just by looking at them that the amount of engineering that went into this one was different to the amount of engineering that went into this one. You can bet if this was an IKEA shed, it will have been engineered to a certain cost point and the amount of wood that was going into the beams would have been calculated so that it was just enough to support the roof and it didn't fall down. This is the tallest building in the world. They will have had models and wind tunnel tests and finite element analysis and everything that you could imagine, different stress testing, different components of the system, all of that stuff would have gone on to build something on this kind of scale because it was new. For software, it's not necessarily evident that there's a difference in scale. So it's not obvious necessarily on the face of it that the engineering that goes into building, I don't know, software for my mum's cake shop should be different to building software for an autonomous car or a medical device or you know, a financial exchange or something. But they would be different. But there'll be common behaviours, there'll be common parts to that engineering discipline if we were to get it right. There would be something that spanned the scale of software development that was applicable across the board. So what is engineering? I've been talking about this for a little while, and occasionally I'll get involved in conversations about things like this on Twitter and stuff like that. And this is a tweet that somebody sent me in reply to something that I posted a couple of years ago, and I've kind of blanked out their name because I disagree with this completely, and I didn't want to disrespect the person who sent it. But so for me, engineering means working in a certified, inflexible process that includes planning ahead a lot, the antithesis of agile. I'm sorry, but I just think that's drivel. I think that's nonsense. You know, if you're building the Curiosity rover, is that working in a certified, inflexible process that includes planning ahead a lot? It's not. It's not engineering. This is confusing production engineering with design engineering. Design engineering is always a process of exploration. That's our game. It's what we are doing is design engineering. We are always exploring the problem. So I think this is wrong. So this is another tweet. I did this talk at a conference in Australia last year, and I got this tweet after the first presentation. Engineering is mostly about construction and automation and tools and processes around it. And I replied to that. I disagreed. No, it isn't. Was the design of the Curiosity rover mostly construction and automation? No, but it was engineering. And I was delighted to get this reply from Anita Sengupta, who was one of the engineers on the Curiosity rover. So, you know, proper engineering, there is a discipline of design engineering where you're not just treading known territory, and that doesn't devalue engineering. So let's look at some definitions. Here's Wikipedia's definition, and there's some words that kind of step out. It's the application of empirical evidence, scientific, practical knowledge, blah-de-blah-de-blah. Here's another definition. So again, practical application of knowledge of pure sciences in solving practical problems. And here's the last one, the application of scientific and mathematical principles to practical ends. So here's my working definition. So for the rest of the talk, when I'm talking about engineering, this is what I mean. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. I think that's a decent working definition. I think that's, that's a reasonable starting point. And I think all of those bits are kind of important. So it's important to be empirical. It's important to be data-driven and kind of using scientific style thinking. And we're trying to do efficient solutions, not just in terms of performance, but in terms of economic efficiency and those sorts of ideas. All of those things come to play. I think that any engineering discipline worth its name in the context of software, for sure, I can't imagine it without these 5 things. It needs to be iterative. It needs to employ feedback so that we can learn and adapt. It needs to be incremental so that we can build up piece by piece. It needs to be experimental so that we can try things out and find out what works and what doesn't work, because we're not always going to get it right. And it needs to be empirical. We need to measure it in the real world, because again, we're not always going to get things right. So I want to explore each of those ideas in a bit more detail. So first, being iterative. Iteration is the act of repeating a process, the first bit's boring, or with the aim of approaching a desired goal, target or result. That's the sense of iteration that we're interested in. Iteration is vital because it means that we can learn, we can react to what we learn, and we can adapt to what we have learned. And I think if there was one idea really that was kind of fundamental to agile thinking, it's probably that. It's that ability to figure out what's going on, adapt to what we perceive and change our behaviour based on what we learn. It allows us to steer towards a goal. It means that we can kind of set some target that we'd like to aim for, and then we can kind of navigate towards it. We can make mistakes. Sometimes we go in the wrong direction, sometimes we go in the right direction, but it gives us a way of navigating towards some desirable outcome. And it allows us to continually improve. It allows us to continually refine the quality of our thinking and our work over time to get better and better and better at something. And that also allows us to exercise ourselves and in the sense of becoming more and more efficient at some aspect. If you're no good at releasing software, you start releasing software more quickly, it forces you to get better and better and better at it. I'm not suggesting that you're no good at releasing software, because from what I hear, you're doing pretty well. But nevertheless, this is part of the reason. By being iterative, it allows us to continually improve. Feedback. Feedback is information about actions returned to the source of the actions. It means that we can observe the impact of our choices. It allows us to, again, reflect on the decisions that we've made and choose alternative paths based on what we learn. It allows us to become more evidence-based in approach. This is what my schematic for continuous delivery. I use this model quite a lot when I'm explaining continuous delivery to people. And it's much more complicated than this. I think the feedback is absolutely, profoundly fundamental to any good development process and is at the centre of the ideas of continuous delivery. But this kind of simplified version is, I'll just explain. So at the outside we have the goal of all software development. Have an idea, get the idea into the hands of users and figure out what they make of it. That's the first feedback loop. In the middle, we've got the kind of test-driven development cycle. We're going to write a test and see it fail, write some code, make it pass, refine it, refactor it, and then commit and move on to the next one. And in between, we've got these user-focused viewpoints on the software, executable specifications, validating our decisions and our choices in the design of our software. I think that if you take feedback seriously and start applying it to any change in your organisation, whether it's organisational, cultural, or technical, you'll get better results. Start thinking about, how will I decide whether this was a good idea or a bad idea? I'll close the feedback loop so that I'll understand. Incremental. Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design application in which components can be freely substituted if someone improves or can find a better performance. I want to tell a little bit. So my wife tells me that I'm a serial nerd. But she's wrong, because I'm a parallel nerd, because I can be a nerd on multiple fronts at the same time. One of my nerdisms is the space program, and particularly the Apollo space program. And so I want to talk about modular systems in the context of the Apollo program. The Apollo system, one of the insights that they had, they didn't have this idea right at the beginning of the program, but one of the insights that they gained was the idea of making a modular system. That was an important step forward in being able to engineer something on this kind of scale. This is the first module. This is a Saturn V, the most powerful rocket that we've built so far. Elon Musk's supposed to be building a more powerful one, but he hasn't yet. This bit of the spacecraft is just to take all the rest of it from Earth to Earth orbit. Big problem, lots of spacecraft to get you just into Earth orbit. This is the command module and the service module. This bit is aimed at getting from Earth orbit back down to Earth. And this bit is about getting from Earth orbit to the Moon and back. This is the Lunar Module. The top bit is the Lunar Ascent Module. That was from the Moon to lunar orbit. And the bottom is the Lunar Descent Module. That's from the lunar orbit to the Moon. Without that, they couldn't have built the spacecraft because just the energy budget was too high. The original concept of sending people to the Moon was essentially a Wallace and Gromit style spacecraft that took off from the Earth, flew to the Moon, landed on the Moon, took off from the Moon and landed back on Earth. That was kind of the 1950s picture. But that's not very energy efficient because you're lifting a lot of mass and moving around. So by discarding mass and modularising the system, it allowed them to solve the problem. Also, this is a much more configurable system. When the Apollo 13 disaster happened and the service module exploded, destroying the spacecraft, it was only by reconfiguring the other parts of the system that they were able to get the astronauts back safely to Earth. The other part that's important about incrementalism is the idea of batch size. Batch size is one of these process technical terms that's used in lean thinking quite a lot. And lean practitioners talk a lot about reducing the batch size in order to work more effectively. Essentially what we're talking about here is making change in many small increments rather than fewer larger increments. And there are some good reasons for that. The data says that's the safest, most effective way of making change. And there's some good reasons for that. I apologise, this is my bullshit mathematics, but it kind of just is maths just to kind of make a point rather than be technically accurate. So the total risk of releasing change into production is going to be the risk of a particular change having a defect in it. Okay, so there's a risk that this change might go wrong. And if we've got many changes, it's going to be the sum of all of those risks. So each little bundle of change has that little element of risk associated with it, and that's the part of the total risk. But that's not all there is to it, because there's also the risk that two or more changes might interact in unexpected ways that might introduce a defect. So we've got the risk of interaction, and that's going to be some function of the number of changes. And so in this formula, n is a significant number. The number of changes makes a significant contribution to the total risk of going into production. So a way of reducing risk is reduce the batch size. Many small changes are less risky than fewer big changes. This is backed up by evidence from production. Amazon pushed change into production once every 11.6 seconds, and since they've been doing that, seen a dramatic reduction in problems as a result. So we're essentially saying, if you've got lots of changes like this, n is very large, and so the risk is very large. And if you've got fewer small changes like this, n is small, and the total risk is low. This is a picture that I stole from Jeff Patton in his wonderful book, Story Mapping. He describes the difference between iterative and incremental with this picture, and it's just such an elegant exploration. I thought I'd share it. So iterative is like this. You kind of do a sketch of the whole thing, and then over time you refine the sketch until you end up with a completed thing. Incremental is like this. You built it module by module by module, and you assemble the whole out of a series of pieces. I think that you need both of these. If we want an engineering discipline, you need both of these ideas to play. You need to be both working in an iterative manner and in an incremental manner in different dimensions, depending on what it is that you're looking for. Both of these bring significant power to our ability to make software and evolve the change over time. Experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect, demonstrating what outcome occurs when a particular factor is manipulated. So being experimental, I'm going to explore my nerdism again. So I want to tell you a little story, again, based on the Apollo program. So in 1961, JFK stood up in Congress and said, we're going to send a man to the moon and bring him back again. I'm sorry you did say man, because it was 1960s. So he's just kind of set out this vision for what it is that they're trying to do. He's kind of painted this picture. And somebody said to me, is this the most expensive user story ever? I think it's a candidate for that. And at this point, JFK stands up and says, we're sending people to the moon by the end of the decade, and everybody in NASA goes, because they have no clue how to do any of this. They have no idea. When he stood up in Congress, it was 2 weeks after Alan Shepard had been the first American into space. Alan Shepard was an enormously brave man. Alan Shepard was essentially strapped in a tin can on top of an ICBM missile, which were blowing up on launch all of the time at this period of history, fired 60 miles up and then parachuted back down in his tin can. That was the mission. He didn't go into orbit, that was it. And 2 weeks after that event, Kennedy's standing up in Congress saying, we're going to the moon by the end of the decade. So here's some pictures of the things that they didn't know how to do. This is basically all of the things that you need to know how to do. So they hadn't got launches sorted. If you look at a montage of this period of history, this is basically American rockets blowing up on the pad. They hadn't got multi-stage vehicles sorted. They hadn't got docking. Nobody yet had docked to spacecraft in space, the Russians nor the Americans. They hadn't got spacesuits sorted that you could do work in. Nobody had done a spacewalk yet. They hadn't got recovery sorted yet. The next mission, Gus Grissom, his capsule sank, and they had to haul him out of the ocean. So all of these things are unexplored territory. So where do you start with a challenge on this kind of scale? What do you do? Well, you do some engineering. You start thinking very hard. This is the first software engineer. This is Margaret Hamilton. She coined the term. So she invented the term software engineering for what it was that they were doing. But here's the problem. So here's the Earth-Moon system. Except that's not the Earth-Moon system. That's a kid's storybook picture of the Earth-Moon system. This is the Earth-Moon system to scale. So at this point in history, no human artifact had been more than 1 pixel away from the Earth. So the first problem, how do you get something from there all the way over there? You can kind of imagine them the next day in NASA sitting around the meeting room going, I think I could get a job in car maintenance. How are we going to do this? I know, we'll build a spaceship, we'll put 3 astronauts in it, send it to the moon and see if they come back. No, that's probably not ideal. That's probably not the best way of doing this. I know, well, let's build a spaceship, send it to the moon, bring it back, but not put any astronauts in it. Okay, that's better. We might keep our budget for a little bit longer if we do that. We'd learn a lot, but it's incredibly difficult. I've got a great idea. Why don't we just send a spaceship to the moon, land it on the moon, but not bring it back? Wow, that is a great idea. That nearly halves the problem. That's loads simpler. That we could do that. What does landing on the moon mean? It doesn't have to survive the landing on the moon. That was this mission. This is the Ranger program. This was literally spaceships as bullets to see if you could hit the moon. That's what it was. So how did that go? So the first mission, its job was just to put one of these things into Earth orbit. Remember I said that they were having trouble just launching stuff at this point. Predictably, it blew up on the pad. The next one blew up on the pad. If you've ever worked in a large project, the next step might amuse you because they've just had 2 launch failures. Now they say, I know, we're behind schedule now, we're going to go for the moon anyway. So they got it into Earth orbit, they did the deorbit burn, they fired it off towards the moon and predictably missed. Ranger 4, They did it. They got it into Earth orbit. They did the deorbit burn. The spaceship died. But they had no telemetry, no feedback from the spaceship at all. But from ground-based observation, they saw that it hit the moon. The fifth one missed the moon again. The sixth one, it worked. They got telemetry back, but the cameras failed, so they got no pictures of the moon. The seventh one was a success. The eighth one was a success. And the ninth one was a success. So you are NASA. In the Cold War, you've got essentially an unlimited budget in effect. You've got access to the finest minds, the finest engineering talent in the Western world. Can you just imagine being at the end of the phone call, "Hi, it's NASA here, we'd like your help." I'd be on the next plane, I don't know about you, but you know, they could recruit whoever they wanted. Where do you start? Do you start by drawing a Gantt chart and having a 10-year plan? No, that's not what you do. What you do is that you start experimenting. You say, we want to go over there, but does this move us closer or further away? You do a little experiment and you figure out step by step by step. There were millions more. I've told this story for somewhat dramatic effect. There were millions more experiments than this. But that's how you do engineering. That's how you do design engineering. Here's a little experiment in its own right. This is about being experimental. So have people seen this kind of thing before? So the idea here is to figure out which is the larger of the two dots. Hands up, everybody that thinks that orange dot is the bigger one. Hands up, everybody who thinks that orange dot is the bigger one. Some of you have seen it before. Hands up, all those people that think they're both the same. They are in fact both the same. So we can carry out the experiment and we can determine by measurement that they're both the same. Has people seen this one before as well? So hands up all people that think that line is longer. Nobody. Hands up everybody who thinks this line is longer. A couple of people. Hands up who thinks they're both the same. You weren't paying attention, apart from the three people that put their hands up, because I cheated. This line is longer. I made it longer on purpose. You can't tell without measuring. You can't tell, just jumping to a conclusion. We are all programmed to just jump to conclusions because biologically that makes sense. If you're living out on the savannah and something seems to be moving in the distance, do you do a detailed analysis and a comparative sampling of whether that's a lion or not, or do you run away? You run away. You go, that's a sensible survival solution. So we are programmed to jump to conclusions with incomplete evidence, which doesn't prepare us well for the modern world. Being experimental means doing away with our propensity to fool ourselves and instead starting to become more evidence-based. We want to be empirical, based on concern with verifiable by observation or experience rather than theory or logic. I think software development is kind of interesting. I think software, in my experience, tends to appeal to the same kinds of people that find maths appealing. We like maths, most of us that do this kind of thing. And so we tend to think highly of maths. But even today, when we've got these massive software simulations, we do all sorts of maths. How does Boeing test their jets for the first time? They put the engineers that design the jets after the immediate test flights, they put the engineers that design the jets in the back of the aeroplane and they go flying on the test flights. It's become kind of a ritual, but you can't really, maths is only as good as the accuracy of your simulation. It's always an abstraction. And it's a wonderful, powerful abstraction very often, but it's not enough on its own. Until we can verify it with observation and measurement against the physical reality, we don't know whether it's accurate or not. So going back to the reality is always important. Sorry, definitions. Being empirical is really important because it means that we can start to separate the myths from the truths. It means that we can start to become genuinely practicing something that we could think of as being science. It means we can make evidence-based decisions rather than guesses, really. Being empirical means that we can never be certain of success, and so empiricism is part of our defense against that. Progress comes only when we risk failure, and so we've got to take the chance. We learn the most when our assumptions are not met. If we come up with an idea for an experiment and our experiment fulfills our expectations, first, we haven't learnt anything new because we already started off with the expectation. And second, that might mean that the experiment was rubbish or biased by our predisposition to believe something. So science tells us that the best way of doing things is to falsify things. We should try and prove them wrong rather than prove them right. However many automated tests you have, you can never prove that your software is good. But if you can work in a way so you have one test failure, it proves that your software is not good enough and you can reject the change. We learn when our stuff doesn't match positions. Production is always going to surprise us. However good we are, there are always going to be things that we miss. And that's okay, as long as we work in a way that we can kind of recover from it. And I think it should surprise us. If it's not surprising us, we're not taking enough risks. We're not really being sufficiently innovative. This came to me not very long ago, this idea. In many ways, all of our design choices, all of our coding, all of the ideas in our heads, the documentation, the tests that we have, the code itself, the requirement specifications, the whole lot are only ever our best theory at the moment of what should be really the case. And the job of software development is to continually refine that theory and improve on it. And again, that's like science. Science, I'm one of my other nerdisms is I like reading about physics. And general relativity is this beautiful, staggeringly wonderful idea about how things work on the grandest scale in the universe. Bendy sheets of space-time defining what's going on, and the gravitation bending the space-time continuum, and that's the way it works. And yet we kind of know it's wrong, because it doesn't fit in with that other amazing theory, quantum field theory. They don't match, they don't meet up. So we know it's wrong, and there are teams all around the world that are currently funded trying to find a better explanation, a better description of what's going on. And that's a good way of us working. It's the best theory to explain things so far, and our job is to continually refine our understanding. Going back and changing what we thought before is not an admission of failure, it's an admission of success. It means that we've learnt more and now we have a better understanding. So, where do we stack up with this fundamentals of an engineering approach? I want to evaluate this from a different point, continuous delivery as an engineering discipline. So is it iterative? It absolutely, at its foundations, is iterative. The whole point of a deployment pipeline is to give us an opportunity to move very quickly and iterate very quickly on ideas and changes and evaluate them. It's built on the ideas of feedback. It gives us opportunities to learn and adapt based on changes at the fine-grained level, sort of test-driven development level, and at the coarse-grained level of getting changes out frequently into production and understanding what our users make of those changes, and being able to refine our understanding at the business level as well as at the technical level. It's incremental. It allows us to build up systems over time and manage the dependencies between them. It's experimental. We're able to carry out experiments in multiple ways. I think one of the enormous benefits that we have as a profession compared to other professions is that we have these amazing machines that are almost the perfect experimental platform in which we can evaluate our software. We can simulate almost anything. We can put our software into little test rigs and evaluate it and probe it and measure it and understand exactly what's going on with it, if we want to. And it's empirical. We are never ever going to get it right. There's nobody on the planet that can predict a system of any complexity in all of its behaviours, and so we're always going to be learning from it, and we should be expecting to do that. So, continuous delivery is about short feedback cycles, test-driven development, automation, it's hypothesis-driven, and it uses tests as a falsification mechanism. It establishes these feedback loops that we talked about before. Fundamentally, the way that I think about continuous delivery is it's absolutely grounded in this. And I'm sure that this is familiar to nearly everybody in the room. This is the scientific method. We're going to make an observation. From that observation, we're going to propose a theory. And from that theory, we're going to make a prediction. And then we're going to carry out the test of that prediction and see what happens. And that's going to change our observations, and we're going to go around the loop, and we're going to go around the loop. We have the ability to operate this at enormously accelerated scales as a series of small tests, as a series of larger tests, as a series of evaluations going out into production. But we can start applying the scientific method to software development. And if that's not a good definition of software engineering, I don't really know what is. We've learned over the years that if we want to do software development well, it's simply not good enough to treat these things as a series of different distinct steps. These are continua, and if we want to do good software development, we're going to be doing all of these things all of the time. It's going to be a continual process. We're going to iterate through this process of design, develop, test and release, design, develop, test and release, and part of the game is to optimize to make that as effective and efficient as we can. We can, if we start this sort of thinking, we can start measuring things. So, for example, this represents the cycle time, how long it takes us to go through one of these loops, and that's a good measure of the efficiency of our process. It's also a wonderful tool. Driving for shorter cycle times is a very effective way of driving good process behaviours inside your organisation. It also means that we can start applying these experiments. We can carry out an experiment, we could have a theory, we can make a prediction in the form of some working software, we can get that out into production, and we can see what our users make of it and make some new observations and inform our development from there. Or we can have a theory, we can make a prediction, and we can make an experiment and an observation inside our test harnesses and evaluate our software there. It gives us this experimental platform. So I would argue that continuous delivery is a genuine engineering discipline for software development. And as I said earlier, as you would expect, if I were correct, we see quite dramatic improvements in productivity, efficiency, quality, and also the enjoyment that people have working in this kind of environment. One of the number one predictors of organisations that are doing continuous delivery versus those that aren't is job satisfaction. Because people enjoy working in this way, because it's creative, it's inventive, it's less stressful because we're working in a disciplined manner. When I first started presenting this kind of thing, I got pushback from the craftsmanship community, because the craftsmanship community had moved the game on a little bit. They've got some good things, and there's a lot of them. There's a lot of craftspeople out there. And they talk about the importance of these things: skill, creativity, freedom to innovate, the ideas of apprenticeship schemes and all that kind of stuff. And I don't disagree with any of these things. I think it's really important to be able to do all of these things, to be able to have an effective, disciplined approach to software development. But I think all you have to do is change one word. It's not that craftsmanship's a good thing. Engineering is also a good thing. These things are equally applicable to an engineering discipline. Engineering adds to craft. It gives us improved repeatability. It provides guidance and structure when we're stuck, when we're not sure where to go next. We can say, well, okay, so what do we observe? What's our theory? Okay, it's this. Well, if that were correct, what do we predict? What's the experiment? And that gives us a way of moving forwards in an organised way. It improves the quality dramatically because of the feedback cycles and the information that we gather. It allows us to build much higher quality systems. It improves the efficiency of the process because we can move quickly with stability. We can try out innovative ideas quickly and cheaply in simulation and in test. And it gives us an approach to solving problems when we're stuck. Because again, we can go back to the kind of scientific method and first principles. The final thing that I have to say is that I sometimes say, okay, so engineering is such a poor analogy or such a good analogy for software development. I'm not talking about analogies. So I'm not saying be like engineers. What I am saying is that we should be engineers. We should take on the mantle of engineering, and that means approaching what we do with a little bit more discipline, a little bit more rigour, a little bit more kind of scientific kind of application to our work. That's my talk. Thank you very much. We have a little over 10 minutes for questions, I think, on the schedule. So I'd be more than happy to take any if anybody's got any. Stunned silence. You all agree then? Good. Results.
There was another analogy I read and liked very much. Rather than being engineers or architects, software developers are somehow like city planners.
Mm-hmm.
What do you think about that analogy?
So my problem is that I don't think engineering is an analogy. I think city planning is a reasonable analogy. I think it is, I'm not talking about engineering as an analogy. I'm saying it's an engineering discipline. If we do it right, it can be an engineering discipline, and that's a different kind of thing. So the city planning thing is kind of interesting, and if you do city planning properly, you do it empirically. You do it based on data. You collect the data, and you could think of that as a kind of engineering, I suppose, in a way. I think our kind of engineering we can do with a bit more rigor than that because we have a bit more control in the systems, because software systems ultimately, are in our control. We can decide the degree to which they are deterministic or not. We can decide the degree to which they are scalable or not, and we can measure those things. Yes?
With the interaction you normally get with a product owner, craft is something that they inevitably comprehend fairly easily.
Yeah.
Albeit it's a bit difficult getting past the Prince 2 waterfall stuff into the real world. When you go into more of the engineering aspects of it, do you find that more difficult to get into the product owner's head, or is it you get a different type of product owner involved?
If I'm honest, this is not a pitch that I make to product owners very often. I think that it's. I don't think of it as sneaky. I think it's honest to have different kinds of conversations with different kinds of people. So the things that product owners and more commercial, let's say more commercially focused people. So more. I don't like the division between business and technology very much, but let's use the words sort of more business focused people. I think the right conversations to have with them is what's the impact on the business? What are the commercial impacts? What in terms of efficiency, their ability to deliver what customers want. And I believe it's my job as a technologist to apply my expertise and my craftsmanship, for want of a better term, to maximise that capability. And what I believe is the case is that applying engineering is the best way to deliver on that promise. And the data backs me up. The data is quite staggering. So there's a thing called the State of DevOps report, which has been doing analysis of the software industry for about the last 5 or 6 years, I think. And they've been collecting data, and this is peer-reviewed analysis of performance in the software industry. We've not had this kind of data before. And it says things like organisations that do this make more money than organisations that don't. It says things like you're going to see high-performing teams spend 44% more of their time on useful work. So this is the way of being more efficient. This is the way of satisfying the product owner's demand. This is the way of delivering the impact that they want. Now, it shouldn't really be that, if we believe in the agile thing, that, we want the people that are doing the work to have autonomy to make choices and decide how to best to organise to do the work. It shouldn't be the product owner who's deciding whether I write tests or not. That's not their job. It's my job. My job is to decide how to most efficiently deliver value into production. Their job is to tell me which bits of value they want delivered. So this is up to me, not to them, really. As a technologist, that's the way that I perceive it. I don't very often have that. Sometimes I have that conversation with product owners, but I think it's important to understand where the value is. They are mostly what my experience has been that when you kind of take away some of the technical things from product owners' purview, they're usually relieved because they don't really want those responsibilities. They just feel like they ought to be having, it's their responsibility. But it's not. So I think we should be moving out. If somebody employs me and they say, we want this really quickly, so don't bother writing all that testing nonsense, I'm not going to do that. I'm sorry, because I go faster if I do all the testing nonsense. So that's the way that I justify it to myself. Thank you. Yes?
In one of the slides, you mentioned the difference between iterative and incremental approach, but whereas at the end of the slides about continuous delivery, you said it's incremental and iterative.
Yes.
How does that work?
So you use both techniques in different places. So so for example, let's imagine that we've got a greenfield project. We're on day one. How do you start a project when you've got nothing? Well, the way in which I start a project when I've got nothing is that I'm going to carefully select a nice, simple story, a nice, simple requirement. And I'm going to use that nice, simple requirement to allow me to build my test infrastructure, my deployment infrastructure, and all of that sort of stuff. I'm going to write some unit tests, I'm going to write some acceptance tests, I'm going to write some deployment tools, just to fulfill this simple thing. So that first story is going to be the Mona Lisa sketch, the full sketch. So the utility of that feature is going to be tiny. It's not really very useful. It's not really a very good picture of the Mona Lisa yet. And I'm going to add more features on top. Once I've built that thing, there are going to be new things. So that's the incremental stuff. So I've built this first feature, and over time I'm going to refine that feature and make it better and better and better. And I'm going to make my infrastructure and test infrastructure and deployment infrastructure better and better and better over time. But I'm also going to be adding new features on in different parts of the system as I learn about the need for those things. So I think you need both techniques, and you apply them in different places, but they're kind of complementary and reinforcing of one another, I think. Pleasure. Yes?
Does your engineering view have to say about documentation?
So I think it depends on the documentation. I am a believer in the agile mantra, which is don't write documents that nobody's ever going to read. That's just waste. So I think it depends on the nature of the documentation. So first, when's the last time you read the documentation for Amazon? You know they're changing it all the time, and you don't care. So there's at one level for certain kinds of systems, if you're making tiny small changes, the system kind of naturally moves at a relatively slow pace from the point of view of the user. There's never any big bangs or anything like that. Okay. Right. Okay. Fine. Gotcha. So if you're talking about technical documentation, so then what I'm interested in, there are usually two levels of documentation that I'm interested in. Part of my background is working in regulated environments, so finance and healthcare and those sorts of places. In those, there's a certain demand. There's a certain level of documentation that you must exhibit in order to make change. And the secret to that, I think, is to make the documentation accurate but vague enough that you can carry on working without having to change the documentation all the time. So that's what we did when we built our exchange. We had a high-level, vaguely fuzzy picture of our architecture, and nearly all of the changes still fit within that map of the architecture that we ever did over the 5 years that I was there. And that's one strategy. And then there's the other kind of documentation, and there's the stuff that helps you. I think that tests are a really vital part of the documentation of a system. So one of the techniques that I advise that people adopt is to use an approach to automated testing called specification by example, or treating your tests as executable specifications for the behavior of the system. And so they are automated specifications. They are natural documentation of the system. I have a friend that used this approach for an airline reservation system. And if you phone up the airline and you're talking to the support people for help on their reservation system, the documentation that the people are reading in the support centre are the executable specifications for the behaviour of the system. They're the scripts of the tests. What stronger statement is there that the software does this than the test that ran against this version of the software and passed? So there's that part as well. And then there's other sorts of documents which are kind of more informal, that are just helpful to kind of get the context of something. I quite like maintaining what I call a whiteboard model of a system, which is, I call it a whiteboard model because the idea is that anybody that isn't completely junior on the team could kind of recreate it from memory on a whiteboard. So that's intended to put a limit on the level of detail in the diagram. So again, it's vague enough, it's high level concept enough, but it's also useful enough to be able to make decisions about where you're going to put behaviour in the system. So there are those sorts of things. And finally, again, in the regulated regime, a lot of this documentation you can kind of auto-generate. So if you've got a good, effective deployment pipeline, it's almost impossible to build a good deployment pipeline without having complete traceability of your system. And then you can treat it as a search space and you can kind of generate documentation. We used to generate release notes so we used to generate release candidates. We were a bit slower than you. I think we used to generate release candidates every 57 minutes for our entire enterprise system. And we were regulated by the Financial Services Authority as it was then. And so we auto-generated release notes for everyone on demand. When you needed a release note, you just said, do I need a release note? At that point, we'd generate one for you. And it would tell you all of the features that were in there, all of the people that committed against it, all of the tests that were run against it, everything. So I think there's different kinds of take. I think that the idea is the idea, continuous delivery idea is how do you establish the most effective, efficient feedback, and then everything else is kind of subservient to that. How do you get it in the loop? Pretty much, is kind of part of the game. Thank you. Did that address your question? Good.
My background is safety visual software, so I'm the one other person in the room that has any interest in
Sure. So I've been doing a bunch of work recently with three organisations that build medical devices. So that's a very high standard of compliance and regulation for safety critical systems because their machines can literally kill people if they get it wrong. So yeah. If I'm honest, I believe that continuous delivery is the only way in which you can honestly implement a fully compliant system. I don't believe that there's a way of doing it without this level of automation. Because if you rely on human sign-off processes and so on, we are too fallible, we're too error-prone to make it reliable, in my experience. I spent the last couple of decades working largely in finance organisations, and if I'm honest, the vast majority of finance organisations kind of play lip service to compliance and mostly are just kind of sticking, how do we make sure the regulators never see this kind of thing, rather than genuinely solving the problem. Yes.
Has that changed? Because I used to work in finance.
I think in pockets it's changing because of this stuff, but it's still mostly like that, I think.
I wondered if there's a version of this presentation that you give to people to convince them against that behaviour of ticking boxes and.
There are other presentations that I use for that. I don't really know why, but I get involved quite a bit through my consultancy in advising those sorts of organisations and talking to regulators to convince them that this is a good idea rather than a bad idea. On the whole, that goes down surprisingly well. Mostly regulators and compliance people, once you start exploring the ideas, they go, oh yeah, that's what we want. But it takes a little bit of an open mind because mostly regulations kind of built around the assumption of waterfall, and so it takes a little bit of an open mind. But mostly they know that it doesn't work. As we were just talking, in the finance industry for sure, but also in the healthcare industry, sadly, I'm sorry. but mostly those sorts of systems don't work very well. The traditional sources. There was some lovely data from the State of DevOps report last year that if you have a change approval board, that is negatively correlated with software quality. So if you have got a change approval board, you are more likely to have more bugs in your system than if you don't. That's kind of worrying. So the most effective, the most highly correlated approval process with low bug counts is informal peer review, pair programming, something like that. Yes.
So in Whiteboard we've had stuff in the past, and they had with the manual testing, they always had 2 or 3 people doing the testing.
Yep.
With obviously automated testing, do you ever do multiple different testing systems, or do you always rely on one testing system? Like if there's a bug in the testing system you're using, how do you kind of counter that, or do you not counter that?
So what we did with our exchange was that when we were developing new software, we would have a human being for the first time. They would manually verify the behaviour of the system that the test was asserting, as well as the test, and then from then on we'd trust the test.
Okay, so once you knew that it had been verified, that the automated just carried on.
Yes, there's no point repeating that after the point. After the point was what we thought, and again that was kind of a regulated. That was in response to a regulatory need more than anything else. I'm not quite sure it adds anything much to the quality. I don't really believe that very much the independent verification thing. I'm not quite sure that actually does add very much value if you get the testing strategy right. I might. That's just. I have no data for that, so I might be just making this up.
That's fine. So a lot of cases there was double entry.
Yes.
And if they didn't quite 100% they have to do a third entry to see who was wrong and then go through.
So the approach that I recommend, I was recommending to some folks this morning from your organisation, the approach that I recommend is driving the development from testing. And when I talk about the engineering discipline around some of this stuff, that's part of what I mean. And so we test that the test is valid by other means. So we run the test and show that it fails before we allow it to pass and all that kind of stuff. So I think that's a slightly different game. One of the things, most of the build management systems like Jenkins and TeamCity and Bamboo and those sorts of things, most of them have a feature that you can turn on that says if a test fails, run it another 2 times. And I think that's nonsense. Because if it lies to me one time, how do I know whether it's lying when it's passing or when it's failing? It's lying one way or another. And so I want something more definitive than that. And I think part of the way in which you get that is through this kind of driving the development process through automated testing, rather than seeing testing as a validation afterwards, I think.
So leading on from that then, what value would be placed on integration tests that are probably more flaky than unit tests that tend to be, once they pass, unless there's something really.
So do better integration tests. So I think the stuff we were talking about this morning, I think there are 2 different dimensions that are kind of a minimum to evaluate software from the perspective. The first one is kind of the technical dimension, sort of TDD, sort of unit test style testing. It's the equivalent of a mechanical engineer. Is the tensile strength of this bolt correct, kind of thing. And then there's the Jeremy Clarkson style of driving the car. Is the wing mirrors nice? It's the whole system approach. And I think you need that external approach, that external viewpoint as well. So you need the kind of the developer-centered testing and the user-centered testing. You need both of those things. The approach that I recommend to acceptance testing, I think it helps to mitigate some of the problems that are common with large-scale functional testing that I think you're alluding to with the integration test. And we talked a little bit about that this morning. There are some approaches using creating domain-specific languages and laying the test infrastructure appropriately to separate the concerns so that you can capture these executable specifications in a way that says everything about what you want the software to do without saying anything about how it does it. And then you layer this in a way so that lower down in the guts of the system, it translates that into how you interact with the system under test. And that allows you to move quite quickly and build tests upon shared stuff that's used along a body of tests, and over time that allows you to address flakiness and all those sorts of things. You track those things and you stay on top of them and you eliminate them eventually, and your software and testing infrastructure becomes more and more deterministic and better as a result. I think it's not easy, but the downside, I should say that, I think that continuous delivery is a profound improvement in quality, productivity, bug reduction, all of those sorts of things. But it's bloody hard. It's difficult to do. You've got to be good at quite a lot of things to make it work.
So leading on from that comment, so your exchange, would you have tested that actually fully up and running as an end system? Or would
We
you
did.
walk out, oh, you did do that?
Yeah.
And was that bloody hard?
It was quite hard, but we did it from day one, and so it grew. So if I described our deployment pipeline and you look at it, you go, I've seen people do this. You'd look at it and you go, because it's quite impressive. We had a grid management system that run that test time around allocated tests. We had performance tests that ran at 5 times production load, and all sorts of amazing stuff that was going on in the testing of our software. But we grew it up in loads and loads of little steps over a period of years. So we started off, the first time was trivially simple. I think we had 2 servers. We had a continuous integration server and something that we pretended was production to deploy to. And we started there. And then over time, we got bigger and bigger and bigger. In the end, we were managing a grid of about 50 computers for all of to run all of our tests and all of our test scenarios. We were running about somewhere between 60 and 70,000 tests on every commit.
And how long would the big end sort of test?
57 minutes was our cycle time to releasable software.
That's the full cycle time?
Yeah, including performance tests and everything.
Because we found, I worked with James who asked the original questions, our integration tests are very slow and quite flaky. We have a system that we can't really control, and that's part of our problem. So
I think one of the secrets of automated testing of this kind is to decide where the boundaries of the test are. So what's the stuff that you're responsible for, and draw a very clear line around that, and test only that, and fake everything else. Yeah, you can't do. It's kind of obvious when you think about it. You can't do full end-to-end testing, because that if it's fully end-to-end configured, there's nowhere for you to inject and collect data. So I always have this mental image of kind of putting my software into a test rig, and I'm going to plug it into this system where I'm going to measure it, and that is right at the edges, at the boundaries of my system, using its natural interfaces. As far as my software is concerned, it's deployed in production. It can't tell the difference, but anything outside of my software is faked. In our case, including time, so that we could fast forward through time. But any more questions?
As a previous chemical engineer now working in the IT industry, I might do.
Good, thank you very much. I often get that kind of feedback from engineers and scientists. If there's no more questions, then thank you very much indeed for your time. Thank you.